Every day we benefit from the sun's consistent nature. The sun rises and sets, and our globe is bathed in its constant and sustaining energy. Life's very existence depends upon the light that Earth receives and the well-balanced parameters of the sun's size, its temperature, distance, and mass. All of them very important to the Sun-Earth relationship. First, in terms of its physical size, the Sun is by far the largest object in the solar system. The Sun is approximately 10 times wider than Jupiter and over 100 times wider than Earth. Its volume could contain around 1 million Earths. The Sun is also a massive object. If you were to add together all of the mass for every object in our solar system, the terrestrial planets, the gas giants, the dwarf planets, all of their moons, the asteroids, the comets, the Sun by itself would still be far more massive. In fact, the Sun contains 99.866% of all the mass in our solar system. Being the most massive object, the Sun acts as a gravity anchor, holding all the planets and dwarf planets and objects in their respective orbits. From our perspective on Earth, the Sun appears as a bright yellow disk. The part of the Sun that we can see shining so brightly is called the photosphere. This layer is often described as the visible surface of the Sun because it's the outermost opaque layer, restricting our view of the Sun's deeper layers. Now, while we use the term surface, we're not saying that the Sun is solid. Rather, that the Sun is composed primarily of hydrogen and some helium in a very highly energized state of matter called a plasma. The photosphere has a temperature of 10,000 degrees Fahrenheit, and it radiates dominantly visible light. If you were to take a picture of the Sun, your picture would show a mostly featureless ball. But remember, don't look directly at the Sun without special protection. The Sun emits all the colors of visible light: reds, oranges, yellows, greens, blues, and violets. If all of these colors were equally emitted, then the Sun would appear a very bright white. But instead, the Sun appears a yellow because the peak wavelength of its output comes from the yellow range. The spectrum of sunlight that Earth receives is finely tuned for life to thrive. The Sun's visible light outputs peaks in the yellow-green range of wavelengths. The solar spectrum effectively covers the major wavelengths needed for photosynthesis. This absorption of specific wavelengths of sunlight powers the critical, life-sustaining process of our planet. Earth would not be able to support humanity and the abundance of all the other life if this single process of photosynthesis did not function and proceed at its effective level. Keep in mind, the visible light you are seeing is only a small portion of the full spectrum given off by the Sun. Visible light is only a particular radiation energy range in the full electromagnetic spectrum. Every day we encounter and even use many of the other energy ranges, from listening to the radio, to popping popcorn in a microwave oven, to the infrared motion sensors in our houses, or having an X-ray image taken of a broken bone. The Sun actually gives off varying amounts of all of these energies. The amount of energy that Earth receives from the Sun is approximately 1,400 watts per square meter on our surface. It is so consistent that it is referred to as the solar constant. Aspects of the Sun's design can be seen in its consistent nature, both in its role as a gravitational anchor for the solar system, including Earth's stable orbit, but also in its role as the constant source of Earth's life-sustaining energy. But the Sun is not silent. It has a dynamic nature as well. And the Sun's dynamic nature provides a view of its complexity and its design. The surface of the Sun is constantly churning like a pot of boiling water. Large columns of matter rise from the hot interior while cooler regions sink back down. This convective motion creates granulation, an effect seen at small scales within the photosphere, where cell-like structures or granules form with hot matter surrounded by cooler boundaries. While we are usually only aware of the sun's consistency from day to day, the sun actually teems with activity, from sunspots to massive eruptions. Sunspots are large dark regions on the sun's surface. They form due to the sun's intense magnetic field. The disturbances cause the surface material in that region to slightly cool and appear darker in contrast to the rest of the photosphere. The interior of a sunspot is still extremely hot, only a few thousand degrees cooler than the rest of the surroundings. The number of visible sunspots fluctuates through a solar cycle, and this cycle follows an 11-year oscillation from a period of low activity, called a solar minimum, through a period of high activity, called a solar maximum, and then back to the minimum. During a solar maximum, there can be hundreds of sunspots, and sunspots are often the precursors to a variety of other active features. Outbursts of hot gaseous material can occur from the magnetically disturbed sunspot regions, extending thousands of miles above the surface, forming prominences and filaments, coronal loops, coronal streamers, and even coronal mass ejections. These larger, outward extending features occur above the photosphere in the sun's less dense upper atmosphere. Prominences and filaments are two features mainly seen within the chromosphere. And essentially, they're the same features seen either face-on or at an angle. Prominences can appear as dramatic bursts of material looping off the side of the sun. The looping path that the material takes follows a strongly distorted portion of the magnetic field. Similarly structured to prominences, coronal loops are even larger extensions of heated material that follow magnetic field lines extending out into the sun's atmospheric layer called the corona. Amazingly, this outer atmospheric layer reaches temperatures of 1 to 2 million Kelvin, being superheated by the solar wind and the magnetic storms. Sometimes we use the term space weather to describe various fluctuations and changes in space, especially that affect us here on Earth. Most of these fluctuations originate from the active nature of the sun. The mechanism that drives the occurrence of space weather is a feature known as the solar wind. While space within our solar system is nearly a vacuum, there is a continuous flow of particles streaming outward from the sun, and this forms what we call the solar wind. A continuous wind of particles that travels at incredible speeds, 1 to 2 million miles per hour. However, episodes of extreme space weather occur whenever a coronal mass ejection, or a CME event, occurs on the sun. CMEs are concentrated bursts of highly energized matter that is ejected from the sun in these eruptions of solar flares. If such an event happens in the direction towards Earth, then we are showered with literally hundreds of millions of tons of charged solar particles. Though the sun can be wildly active, can cause extreme space weather conditions, its dynamic nature actually helps to demonstrate just how privileged our planet really is. We live day to day with very little noticeable impacts into our lives. And some of the most observable consequences to this intense solar activity are the beautiful auroral lights that dance across the skies near the Earth's polar regions. Remnants of the massive solar eruptions that were safely deflected by Earth's magnetic field. Yet these few particles that were caught spiral down and interact with atoms in our ionosphere, releasing emissions of visible light. Earth's protective layers of safety were designed in concert with the sun's nature to supply what is needed for humanity's existence.